Hello, this is Mr. Huber. In this lesson, we're going to look at solving exponential and logarithmic equations. We're going to see how the definition of exponential and logarithmic equations, how they can be written in each other's form, can be useful. And also, we're going to see to start here how we can use properties of exponents as well. It states here, if we know that m to the x power equals m to the y power, m would be the same number, then x and y have to be equal as well. You can't have 5 to the third power be equal to 5 to the eighth power. Right? If you have 5 to the third power, it'd have to be 5 to the third power as well. So we can use that to help us in solving these exponential equations we see below. Number one is 5 to the x equals 125. So what we need to do here is get the same base. If we have 5 to the x, we need to get 125 to be 5 to some power. So 125 is 5 to the third power. So we can write this out as 5 to the x equals 5 to the third, which means x equals 3. In the next example, we have 3 to the power 2x plus 5 equals 27. So 3 to the 2x plus 5, we can keep that part the same. We're not going to change it at all. And then the 27 would have to be 3 to the third power. So if we have the base 3, erase that there. If we have the base 3 and base 3, that means the exponents would have to be the same. 2x plus 5 would have to be equal to 3. So we write that out as another equation here. We have 2x plus 5 equals 3. Okay, so now we can solve that equation. We subtract 5 from both sides. We get 2x equals negative 2. And then we divide both sides by 2. And so we have x equals negative 1. And you could plug it back in, just like you would any other time. If we take a negative 1 and plug it back in here, 2 to the negative first would be negative 2, plus 5 would be 3. So we'd have 3 to the third power equals 27, and that is true, it does work, and so we would know that that works out. We solved it correctly. Okay. The next example, 2 to the 4x equals 8 to the x plus 1. So this will be a little trickier when we get that right side over there. When we get that 8 to be 2 to the third power, right? 8 is 2 to the third power. And we'd still have the x plus 1 equals 2 to the 4x. Now here we have to remember what happens when we have a power raised to a power. We're going to multiply the exponents together. So that right side over there, okay, we'd have 2 to the 4x equals 2 to the 3x plus 3, right? We have to multiply those together. Now we could write this out as 4x equals 3x plus 3 because we got the bases the same. Since we got base 2 for both of them, that means the exponents have to be the same as well. We subtract 3x on both sides, and we end up with x equals 3. And if we want to check that, great, we plug it back into the original equation. We have 2 to the 12th power equals 8 to the 4th power. And if on your calculator you wanted to check it, you could put in 2 to the 12th power, and then you could put in 8 to the 4th power, and you should get 4,096 for both of them. You'll see that it's equal on both sides. So again, you can plug your answer back in, check, and make sure that it works. Okay, as I mentioned at the beginning, also we can use the definition of logarithms and rewriting these exponentials as logarithms to help us out as well. So in this first example, okay, 5 to the x power equals 30. If we write that as a logarithm, it would be log base 5 of 30 equals x. Now you're saying, well, that doesn't help me out because at log base 5 of 30, what am I supposed to do with that? Now this is where we use the change of base property, which we've learned. So we'll write that as log 30 over log 5 equals x. And then I can take my calculator and I can actually calculate log of 30 and divide it by log of 5, not 50. And we get x is about, and we'll round to 2 decimal places here, 2.11. In the next example, we need to get that 3 to the 2x by itself first before we start reading something as a logarithm. We just need to have a number to a power. So our first step actually in this problem is going to be to subtract the 7 on both sides. Okay? And that'll give us 3 to the 2x equals 11. Now I can rewrite this in logarithmic form. So I'd have log base 3 of 11 equals 2x. And now when I calculate this using change of base, and I have log 11 over log 3 equals 2x, we're going to have to remember then to divide that answer by 2. When we do the log 11 divided by log 3, so we have log 11, and we divide it by log 3, and just that part should come out to about 2.18. And then you have to divide that by 2. So on your calculator, just divide by 2, and you're going to end up with your final answer of x is about 1.09. Okay, so we got to remember to divide by 2 here. When we get whatever that answer is for log 11 divided by log 3, then we divide that answer by 2 as well. Right, so keep in mind again how we can use definitions, exponential, logarithmic equations to help us in solving these equations when needed. All right. Ceremonial interlude. So when was the tradition of throwing out ceremonial first pitches at baseball games started? You may have seen this many times over the years, throwing out ceremonial first pitches. Most games have somebody throwing them out, sometimes a bigger deal than others. And presidents were actually the start of that tradition. So Howard Taft was the first president to throw out a first pitch, and that was at 1910 at Griffith Stadium. That was a Nationals, Washington Nationals, versus Philadelphia Athletics game. Washington Nationals were around, then went away and came back recently. And the Philadelphia Athletics, before they moved, and are now the Oakland Athletics. So William Howard Taft in 1910 was the first one to do that. There was no photo of that I could find, but I did see this one from a game in 1916. So this is a different pitch that I was talking about. This is Woodrow Wilson, actually. It's still a Washington Senators game. I suppose it made sense for them to throw out first pitches at games in Washington since that's where they were located. And this was against the Yankees there, you can see. And they threw it from the stands. It didn't actually start till a little while later, till the people went out to the mound and threw from in front of the mound, around the mound. So normally that first pitch was thrown out just from the first row of the stands where the person was sitting to watch the game. All right. Let's solve some more logarithmic equations here. So now we can use what we know about that definition of logs and exponents to rewrite this part of the equation as an exponential. Okay? So we know log 3x means it's a base of 10. So when I write this as an exponential, I'm going to have 10 to the second power equals 3x. Well, I can solve that. This is 100 equals 3x. Divide both sides by 3. Divide by 3. And so x is equal to 100 over 3 as a decimal. If we wanted to calculate that out, we can do so in 33 and a third, so 33.3 repeating. Okay, so just looking at the directions to see if we want to give a decimal or an exact answer, 33 and a third, however you want to answer it there. Okay, but again, base 10 to the second power. So now in the next example, again, we have a base 10 to the fifth power this time. So we have 10 to the fifth power equals 4x plus 3. So we'd have to take 10 to the fifth power, and then we could subtract 3. So 10 to the fifth power is going to be a lot of zeros there, right? And then we can divide it, or excuse me, subtract 3 from that. So right, we get our 100,000, because we have 1 with 5 zeros after it. So we have 100,000, and then we're going to subtract 3. Right, so this is 4x plus 3, so I subtract 3 to cancel that out. And so now I'm going to get 99,997, right? And then I can equals 4x. I can divide both sides of that by 4. So I divide by 4, okay, and I divide by 4, and I'm going to get an answer of 24,999.25, exactly, actually, equals x. Okay. So again, use what we know about the definition of logarithms and exponentials to rewrite the equation, and then solve it. When you get 10 to the fifth equals 4x plus 3, solve that like you would have any other time. There's not a logarithm even in there anymore, so you should be able to solve from there. All right. Last couple examples here. All right. First, we have some work to do on the left side of these equations, because we need to condense that down to a single logarithmic expression. Okay, so we can use what we know about condensing in our properties of logarithms. The left side of this first equation here can be written as log x over 3 equals 1. Right? We're subtracting, so we write that as a quotient, x over 3. So now we would have 10 to the first equals x over 3. Right? Base 10 to the first power equals x over 3. We multiply both sides by 3 to cancel that out, times 3. So 10 times 3, 10 to the first is just 10, times 3 is 30, equals x. And if you want, you can check that. Take the 30, plug it back in there for x. Do log 30 minus log 3 on your calculator, hit enter, you should get 1. Okay. And in this next example, okay, we can first take this 2 log x, and we're going to write that as log of x squared, because there's 2 in front. Remember, property of logarithms, we can write that as an exponent. So we're going to have log 4 plus log x squared equals 2. And now since we're adding, we write this as a product. To condense this fully, we have log 4x squared, because we're multiplying the 4 and the x squared, and that equals 2. And now we could write this as 10 to the second power equals 4x squared. So that's 100 equals 4x squared. And so if I divide both sides by 4, I get 25 equals x squared. And now I'm going to square root both sides and get x equals 5. When we square root, we want to be careful and say, well, what about when I square root if I can get plus or minus, right? What if I do plus or minus 5 there? You can't take logarithms of negatives. So if I took this and I had a plus or minus 5, because when we square root, we want to be aware. Normally that means we'd have plus and minus of that number. If I plug a negative 5 in here, I can't take the log of a negative. So I don't need the negative 5. I would just have the positive 5 as my final answer. All right? So we can see how we can use the properties we know about exponents, logarithms, the definitions of them to rewrite equations or get exponents to similar powers that we can write in equations. Right? Some few different things we can see here. Want to practice those different situations. Again, be familiar with the properties and definitions that we can use to get ourselves to be able to write equations then that we can solve. Because they're really the hard parts in those first couple steps of any of these problems. How do I get it down to then an equation that I can solve more easily, like 10 squared equals 4x squared, or 10 to the first equals x over 3, or I have 3 to the 2x equals 3 to the 5x minus 8, and then I can set the exponents equal to each other and give myself an equation to be able to solve.